Let's start.
Yes.
Okay, so thank you for coming today. Today we are talking about AI in large systems. It's a big topic. Actually, I prepared many slides, but I will stick to the times and let's see how. So he gave me 50 hours. I prepared 100 slides for 50 hours just to, to keep it. Yeah. To be fair, I used the 50 hour to the last minute. So anyway, I thought that this is a great opportunity to sum up everything, because I think at the first 3 lectures, there were a lot of things covered, theoretical, machine learning, AI things, a lot of things. But now this is a kind of putting everything together. So you might see like some of the concepts coming back. And I prepared not from research perspective, but from learning perspective, as we are going on with this theme of learning. So you can see that I use this. So you can see that the classical machine learning, we are moving nowadays from classical machine learning, in which still we are doing classical machine learning, but we are moving a bit toward machine learning in systems. So it's a combination. Before it was a data, then training, then evaluation, and we were going to this loop again and again. And then a step further, there was this hyperparameter tuning, going deeper and deeper to machine learning, tuning and tuning until you get better performance. But also you do a lot of error analysis. Before it was kind of like try and error, trial and try and come back until you are satisfied, and then training and more training and things like that. Then later on, during 90s, it became like and then during 2000s it became like more systematic. Like you have data and then data ingestion, you ingest the data to the system, and then this is data verification, feature engineering steps, formal steps forward. So it seems like it was like a lot of software engineering concepts, in which we had like a lot of things went well with the software engineering, but now we see systems, AI systems, like software systems. So a lot of things, like in classical software engineering, we do requirement, we take the requirement, then a lot of activities during the requirement, and nowadays we are doing a lot of data collection, explaining the data, fault handling of the data, and so on. Most of these activities are around requirement of software, actually. And then many activities also going on with the process that we have in software engineering. And also we have architecture of systems. We have a lot of things in the architecture. We have monitoring, for example. It's going on with the quality assurance and the implementation also. So you can see that this is the big spectrum of software engineering, in which you have all these activities of software engineering. But now we are reflecting these activities back to the machine learning, in which we have AI systems, actually, to the AI system. So you can see that AI code nowadays is a kind of very small part of the system. And this is very classical. It became classical now, this kind of graph, since used in this paper. So you can see that the machine learning code is a small part of the system, and there are many other things in the system. So you see that a lot of people are engineering the process, since you are putting everything into the system perspective. So you need to, when you put everything into system perspective, you need to instrument and monitor the runtime of the system. And then you have to manage the training, retraining, the cycle of the system. So the system thinking means that how to put this model. So you can see that, for example, the classical machine learning is that you give a bunch of figures, of images, and then you do the training, and then you have this wait update until you get the good model, and you have the good model basically. But the question is now, what should I do with this model? Where to put this model? Before, it was like putting it on a computer and then feeding it with some pictures and getting the result. But now it's not about that. It's about putting it into a bigger system, because if you put it on a website, you have to manage all these access to this website and how you you serve this model. So this is system thinking is that you have to think about the entire ecosystem, including, for example, if you put it in cloud, how you manage this cloud, how you manage the everything. So we will cover these things in this lecture, including the problems that may happen, how to solve these problems. So when you think about a system, we have to think about, first of all, who is using this system, the stakeholders. And then if you have all these components that I showed before, like, for example, the training, the data, how to manage these things. And if your system is giving, if this AI system is giving decision to some other system or to some people, how you manage this feedback when it comes back to you. So, for example, in this ChatGPT, sometimes you have this like and dislike, and then when you press dislike or like, this is a feedback coming back to you. How you manage this data? If you get 1 million feedback, what if you get 1 billion feedback, for example? How you store this feedback? This feedback is also a data. Then if this is a data, how you manage this data, how you use this data again to improve your system. So all these things are important when you do this machine learning or this AI in general. So nowadays it's not about just getting some data on your computer and that's it. You have to think about the whole spectrum, the whole ecosystem. What if you put it in production and then you are in a company, you put it in the company and you give some decision, what if something happened? How you deal with this? So this is also part of the system. As I said, the feedback loop. So you can see that when you integrate with the bigger system, you have many components. For example, here let's see the speech recognition, for example. So the speech recognition, you have, of course, the UI. It's not about the speech recognition, it's about the UI, the user interface. And then, for example, if you want to have kind of, you use the service, you have to pay something. So there is a payment service inside the system. And you have a user account when you create a user account, and you have results, for example, and sometimes you upload your audio, and then you have the data, the database. and you have the management of this database. And each of these components may be stored in somewhere. So it's a kind of very complicated now with these components. And you can see that actually the machine learning or the AI is a very small part of this big system. But in order to put this small part, this speech recognition into serving, later on we come back to what we call it. In order to serve this speech recognition, you have to manage all these components. So you have to update to obtain the data, for example, how you obtain the data. You have to, if you have a large amount of data, where do you store this data? If it become a big data, what should you do with this big data? Do you need a cloud or not? If you need a cloud, how you need a cloud? Which size you want to? So if you develop a software system including AI, how much it costs? How much it costs when you put it on cloud, and then every time you call this service, how much it costs you? This is a big area nowadays people are studying, and how to maintain. And from time to time, you need to update this speech recognition. How you do this with this update? What you do with the old version? What you do with the new version? How you put the new version not interrupting the system? All these things are actually part of the work, even if it is not part of the training and learning system. So a big part is also this interaction with the outside world, with the users, and then you get this feedback, how you manage this feedback, how you use this feedback as a two-way interaction. Also, the user interact with the system, they like it, they dislike it. You collect this feedback. Can you automate this in order to improve the system or not? How you do this? Also, this is a big part of the system. Also, the thing that we are working a lot nowadays, which is like the drift, how you do this. We cover this later on. So all these things, if you have a feedback, can you detect error with this feedback or not? Can you detect error automatically with this feedback or not? If you detect an error, what should I do with this error? All these things are questions when you design machine learning systems nowadays. Even these questions are not related to data and model of machine learning, but all these are quite related questions and part of the ecosystem. So you can see that we are thinking very systematically as a pipeline thinking, the production in which we want to have this to collect this model requirement, and then you do the data collection, the data cleaning, you do the labeling of the data if you don't have, and then you have feature engineering, back and forth, then model evaluation, and then you put this model into deployment, in which the what we call it the system. So you put the model into the system, and then you monitor it. But we want to keep an eye on this system from start to the end, in which we want to repeat this process again and again when we need it, but we want to make it automated. So in order to do this, you have this machine learning pipeline, or let's be general of and say AI, this AI pipeline, but also you have this monitoring, and you have these small triggers always, in which if something happened during the monitoring, you activate the triggers to do something in the pipeline. For example, if some data error happened and you want to go back to the data cleaning, during the monitoring, you are monitoring the data error, And then when data error happens, then you activate the trigger comes back to the data cleaning, do the cleaning again, continue the pipeline and put it into production again. So if that's the monitoring. So the monitoring is a very important part nowadays in the ecosystem, in the machine learning ecosystem. And you can see that most of the machine learning nowadays is going to what we call it online learning, in which things are going to be automated. So there are many challenges, of course, if you do it offline and online. Offline, of course, is better. It's not better, but it's cheaper and less complex. And but the problem is that maybe you have less applications. It's good for image, for example, things like that, image recognition. If you have like a factory, continuous production, continuous the things that we were working in continuous steel production, whatever, or you have the finance, you are monitoring price of something, you want to make decision very fast. So the online learning is important here. Of course, you have a lot of tools for online and offline. For example, one of the things that we learned during the past lectures is this sklearn. For example, you do the training and everything online, offline. And then if you have the model, you put the model in production. But in the online, you have to do many things online in the cloud, for example. Immediately now, the data is coming, you have to do something immediately. So there are many challenges. Also, you have computation challenges and so on. Another challenge we have is during the system is this continuous integration, continuous delivery that we have. Of course, we have it in software engineering, but now in machine learning and AI, it's very important, and you should have it when you have a system. This continuous integration is the practice of continuously integrating the code. For example, you change the code, you change the data. Even the continuous integration now is with the data. The data is coming continuously. It's good to how you integrate this data with the old data. What is changing during this time? So this is the continuous integration. And then if a new data is coming, the system is improving, you have a new system, a new code, how you do this, how you manage this continuous integration. And continuous delivery, that we have this concept also in which if I have a new code in my system, like new code of AI, how to deliver this, how to deliver the new model, for example, how to put this, how to archive the old model and put the new model into production. So we want to do everything. So people want to do everything faster. So this is the case. You want to do it faster. You want to do it automated, and so this is the case. And also, if you have a large system of AI, you have to have this release management. Okay, now you have a system is working, everything is nice, you are happy, but when is the time for next update? Just like software, when is the time for next update? When you update, do you update the user interface or you update the image, the voice recognition that I showed? So if you update the voice recognition, it means you are updating the machine learning part of the system, or you are updating the user interface, which is not related to the machine learning, but it is connected to the machine learning. So you have to manage also the release. Next month, I will do a next release, but I will not update the machine learning. I will update only the software. But what if there is some problem in the software, then you have to have this plan for it. And then if you have, for example, new data is coming, you discovered after 1, 2, 3 months that your model is not doing well, so you have to retrain or you have to do some update. Then you have to do another release of the software, including the machine learning, but it is the software in general, not the machine learning. So you have to have this plan of management for the life cycle for the release, including the how you rebuild the software, how you do the testing, how you do the review, and so on until the production. So if you have a large system, what are the problems of large systems? Actually, there are many problems. I just put some of these problems here. The main problem of systems, of course, in the normal machine learning, classical machine learning, even in the not in the large system, even in a small system also you have these problems, but these problems become very apparent when you have large system. The first thing is the data quality. Of course, this is machine learning, so there are problems related to the data and problems related to the model and related to the whole system, including data and model. So the first problem is the data quality. So in machine learning algorithms and in AI in general, the algorithms designed for ideal cases. And if you don't have ideal cases, you have to make this, or you have to make sure that you have these cases. For example, um, when you implement something, the algorithm assumes that you have all the representation of the data is clean. You have large number of training instances. For example, the feature values are correctly labeled, and you have all the label, you don't have missing data and all these things. And you have this balance of training and testing data and so on, and you have all these features and all these things for the AI. However, this is not the reality, of course. So we have a lot of data quality issues. Some of these issues, for example, completeness. Actually, if you look at the one of the ISO the new ISO documents, you can see that a lot of these quality attributes of data available. So, for example, this completeness, is the data complete, or you have some missing? So you have an Excel sheet, for example, or the data is streaming, but sometimes the sensor is giving sensor is shut down. So some of the fields are blank or not available. So this means that the data is incomplete. So you have consistency. For example, some of the data is duplicated. So it means that the data is not consistent. Accuracy, of course, some of the data is incorrect. The sensor, for example, is giving some fault values. Time blindness, you are assuming the data for today, but actually the data is for yesterday, for example, or there is some asynchronizing of the time. Relevancy, so sometimes it's related to some business goal, but this business goal is not considered in your model. So it's not relevant, actually, the data. So there are many other things, but these things just examples. So the data error, so the data error, actually, there are many definitions of data error. However, the thing is, in your system, you have some definition for some data. You say that this sensor should send data, temperature data between 10 and 20. Anything below that, after that, that's an error. So this is your definition of error of data. So anything not related to your constraint, this is a data error, basically. But there are many other kind of data error based on the definitions. For example, you have some missing value, you have like outlier, you have some standard deviation of the data. All the data is in this range, but some point is there. So this is an outlier of the data when it comes. Duplicate data, some data is duplicated in the system when it comes. Bias, the data is collected and the data is coming only for some minority, for example, or something. So it's quite biased. Redundant value, some redundant value of the application. Sometimes the data is skewed, it's changed, for example, for the representation, and the data drift that we will talk about that later on. Imbalance data, just if you remember the COVID-19, a lot of people still, they are doing that mistake in research, a lot of papers available with this problem, that the positive cases are less than the negative cases, but people are considered both cases balanced. So the model, the machine learning model, the AI model was giving a lot of false because you consider the data balance. So of course the majority and minority. So you have to keep an eye on this when you do your modeling during the system. So this is when you don't have imbalanced data. So this proportion of the data, if you look at the COVID-19 data, you can see that the amount, the portion of the positive cases is much lower than the negative cases. So when you do the machine learning models, you have to take care of this imbalanced data.
So algorithms are sensitive to this imbalance.
Yeah, of course, but you have to. I should say that, for example, deep learning is quite is quite flexible with this, with many things, with rubbish data in general. Deep learning is used to be like, you feed it with a lot of rubbish data, it will deal with it because you have a lot of data. But of course, you have to do a lot of cleaning and this I forgot the name. This is scaling and so on. Yeah. So one other thing is underrepresented data, in which you have some minority inside the class you have to take care of. So for example, these we call it sub-concepts, or the small disjuncts that you have to take care of when you do your modeling, especially when you have big data and you want to take care of these groups. This is also some problem of data. Data bias, it's a very big problem nowadays. We have in system, of course, for example, with large language model, also you can see a lot of problems with data because they train it with some other some minority data, and it gives a lot of racist answers and so on because of the data bias. So there are several types of data bias, of course. This is a big research area. There is this sample bias in which you take sample only from one regional area or from one minority, not taking sample from different places. And also from the measurement bias, sometimes your measurement is not correct. You are taking the data, but the measurement is biased. So for example, some self-reporting, you are taking data from self-reporting, always saying positive things, you know. And reporting bias is sometimes, for example, sale data, only you train it with successful sales. What about not successful sales? You are not trained it very much, so it will lead to unbiased. It will lead to bias decisions. So this bias was not that big issue actually until 2000, I don't know, 15 somehow. Since the data get big and big, and we had this large data. Explainability is also some problem with large systems. Explainability now is a big area also with large system when you have, and actually I think it's one of the requirement from the European Union now for the explainability. For anything you do, you have it should be explainable somehow. This used to be a very big research and very important research area before 5 years. And actually now with this large language model, a lot of things changed in this area, because with large language model, you simply ask the model why I got this answer, then you got a feedback from the model. You got this answer because of this and that. So this is the explainability actually. When I give a picture to to a system and I say, for example, this child is laughing or not, it says like the child is laughing because of these signs. And in the old systems, because before this explainability, it was like, okay, the child is laughing, but why? You didn't know. But this explainability now with large systems, it become more important because you have complicated issues. You have large data is not easy to, it's not about pictures nowadays. The picture is okay, you can see the picture, but what if this is automated? What if this is not a picture? I don't understand a lot of things of this data, but just I want explanation why I'm getting this. For healthcare is very important now. For example, if you ask the large language model, what should I do in this case? It will tell you like, do this. But when you say why I should do this, you get an explanation from the large language model. So this is basically the explainability that we are searching for. Fairness is a kind of related to the bias also. It's about but it's all about the when you don't have when you have unfair data collection, it will lead to not fair. When you have biased data collection, it will lead to unfair decision. So this is a kind of result to each other somehow. There are many types of fairness. For example, you give equal accuracy for all the groups.
You give like demographic party equal outcomes. How to improve this fairness and equality and things like that. There are many techniques, of course. You do a lot of pre-processing, feature engineering, explainability, of course. You collect more data, more diverse data, and so on. Model robustness, we have it in AI large systems. This robustness is, what we mean by robustness means that, okay, now you have this model. This model is trained for some data, but how robust is this to this adversarial training we do? Like, for example, if you have a different data, different cases that the data didn't see, the model didn't see how the model is behaving. So this is very important to have. Let's take a break. Is it?
Yeah.
Yeah.
Okay, 15 minutes. I think that we are facing in a big system, in large system, is the model robustness. As we said, the model robustness is the ability of the AI model or the AI system in general to produce accurate and reliable results. This is the formal definition. So what to do for model robustness or to get more robust? There are many techniques, of course. One of the things is the testing, and we are testing, but also it's a question, your system is robust for what? You have to identify robust for which thing, because robustness means a lot of things. So is robustness for fairness or robustness for what? It depends on the data, it depends how you train, and it's all about the data actually. So if a lot of technique involve like changing the data, for example, data augmentation. You change the data a little bit. For example, you train the data for some images, and then you basically for a very well-known technique is that you train the model for cat image, different cat image, and then you bring these cat images, and then you put a hat on the cat, or you put the glasses on the cat, and see if the model still recognize that it is a cat. So this is a technique to, and if the model doesn't recognize that, so you feed this picture again to the model and say, actually, this was a cat. So you retrain the model basically with the data that is missing. So there's a lot of human in the loop in this process of robustness testing and so on. Another technique is that this defensive distillation, in which you take this defensive idea by adding noise actually to the model during the training. And of course, you can do a lot of things during the pre-processing. You make sure that the data is fair, the data is good, the amount of training and testing is good, and so on. An example of attacks that happened in one paper is very nice. You can see that these guys try to fool the model. Actually, he was wearing this shirt, and you can see that the model recognize all these faces, humans, but the model didn't recognize this guy in between, because it was kind of confusion actually for the model. So this is a kind of robustness that with robustness testing they do. They try to fool the model and then to retrain again actually. So when you integrate with other technologies,
this AI thing, when you integrate it with the other technologies, here it become the because as you know, like this AI was there for a long time, but now when the computation power is getting bigger and larger, and the system are getting more complicated, and the feature, the functionality of the other system are getting good, and then this AI raised up. Otherwise, the algorithms, all the techniques was there for a long time actually. So the integration, of course, you know better than me with this cloud things, but there are many things. The integration with machines, with robots, with all these things, with like this natural language processing, a lot of processing in the beginning of the AI. And now with this large language model even become very interesting because you can do a lot of large language model steps at the beginning to extract data, to do a lot of automated things for you. And then you feed all these steps to the actual machine learning in your industry to get the output. So this integration with camera and so on, that is the most important thing. Cloud and edge, of course, you know better than me this. The cloud computing, the edge compute, bringing the computation near to the customer and so on. So a lot of things is going on in the edge and so on. So this is the integration actually with this is when the real meat is coming up with the AI. Otherwise, AI is just a simple algorithm going on, working on your computer. But when you integrate all these things together, that's the most important thing. So in my vision, AI is just a very small, in many other people vision, AI is just a very small thing. But actually the system is important, not the AI itself. And how to integrate these components, the edge compute and edge AI. Nowadays, we have a lot of edge AI things, a lot of, for example, people are using this Raspberry Pi and so on to put machine learning on these devices. We have also this tiny ML on the devices, and how to integrate all these tiny MLs to deliver some functionality. All these things are the cloud, for example, the cloud AI. Why it is important? Because it can do a lot of things for you without headache, actually. It can do a lot of automated things for you, but you have to pay. That's the thing. So a lot of data pre-processing, data processing, storing, all these things can be done in cloud actually. And you just go to Amazon. We were talking now with Carluan, for example, about Amazon. So you know, you can just put everything on Amazon and Amazon will do everything for you, but you have to pay a lot of money for it. So it's all about how to integrate these things together. And for cloud, for example, the banks, for example, the fraud detection and so on, because they have a lot of money, then they don't care. They put all these services together, and it's just about the wiring of these services. You plug all these components together in the cloud, and that's it. But you have to pay, of course. What are the current platforms we have? We have a lot of platforms actually. There are many platforms. For example, we have Amazon now is leading actually the area a lot with a lot of services. Even I think Amazon people are getting lost in their services as much as services they have. Also, they have a lot of certificates in Amazon, a lot of new certificates coming on, a lot of new features of large language model and so on. So this Amazon Web Services is getting very user friendly also, but It is expensive, it's not, but it's not as much as expensive as Google, for example. Google is more expensive if you go to Google. It's just boost your card when you use it. But you have Google also. One of the good thing with Google, they have this what they call it, I forgot, this Vertex AI, which is a version of TensorFlow. They have this unified tool for many activities of AI, but actually now Amazon also has this, even nicer than Google. And one funny thing is that most of them, they are taking the open source services and they just twist it a little bit and then they make it money. So you know how it works. And also there is this Azure and there is IBM Watson. IBM Watson, the good thing with IBM Watson is that it's just like it's not complicated actually. I used it. It's not complicated. It's just like you go there and you have this Jupyter notebook and the services are very simple, and also it gives you 500 meg for free to try. But these guys, one big problem with the students when we teach is most of the students are not able to, or they don't allow putting their card because when you register, you have to register your Master or Visa card, your bank card. Otherwise, you don't get an account. So that's the big milestone. One of the things that we a few years ago in Prague, I asked the Red Hat, they have partnered with Google, and they created accounts for students without entering the because most of the students refuse to enter the MasterCard. So even, for example, for IBM Watson, you get 500. You can try a lot of things with this 500 with the student. One of the good thing is that also the Amazon, when we had this guest lecture, they create account for the students. So the student they don't need to put their card, but the account is also for 3 days. We asked them for a research account to try many things. The maximum thing we got was 10 days from Amazon, 10 days for free for academic use. Of course, there are many hidden things inside. Maybe I'm not aware of, but it is very nice to have this is one thing I want to tell you, is that it is very nice to have one of these things in our courses. Building partner, doing something for the students, at least for, it was a very good experience with this AI engineering course to have this account, and the students are getting very nice hands-on. But the universities, other universities are building partner and they get account actually.
Which one did you use in the course?
And we use this Amazon Web Service. But in Prague, we used Google actually.
You have more long-term accounts there.
During the course. But here we got like 3 days for the student. The day they taught the student and 2 days just to try. So it's like, it is good. It's maybe from management perspective, when you meet some companies to build a partner to get something. Many European universities are building this partnership and they get account for students as a kind of advertisement also for the companies actually. So another thing with the large system nowadays is getting in healthcare especially, is getting very populated, which is the federated learning. I see a lot of applications, a lot of papers nowadays coming on with federated learning. Federated learning is just machine learning, but actually is good for privacy. You learn from these devices without sharing the data of the devices. You get some portions of data from these devices in the server here, and then you can manage um, these models on each device. So it's a kind of sharing the models, internal of the model, part of the model. The general functionality of the model is here, but the special functionality. So for example, with this Facebook, you have your own model for yourself as a user, but also there is a model for Facebook in general, for this advertisement and so on. So your model doesn't look like mine, but in general, there is a model that manage these other models. So for patient, this is very important. If you have, and this is good for privacy, you don't share data. The data of the patient is still there. You get some encrypted part of this model going to the general model, and there is data sharing between these devices specifically. Yeah, there are many use cases, as I said. For example, for automotive car, each car has a model, but Tesla has its own model, general model, and so on. So there are many applications. So coming back to the machine learning application, as we said, we have database, we have the graphical user interface, and you have the API sometimes that is connected to the machine learning model. And that is the most important thing here, the API. And actually, most of the, not most, but now all the applications that use large language model is communicating through this API. And this is in OpenAI server. And this is the application on your computer or on your mobile. So this is a kind of, and sometimes if you don't have large language model, but you have some other model, and this model is served on our server here, for example. So you have this kind of application. Now, most of the machine learning, large machine learning model applications look like that, because it's very hard to keep the model on the device. So the model is somewhere else in the cloud, in edge, and so on. So in this case, there are different life cycle actually. There is one which is the machine learning related, the model related life cycle of the application, in which you have model 1, model 2, model 3. I don't care. It's managed in the cloud. This model is updated. OpenAI updating their model every 15 days. I don't care about that, but I care about my API and how I communicate. And here I update my user interface, my graphical user interface. I update my data and database and so on. So this is also the general application life cycle, which is a software actually. But here, this is the machine learning life cycle, the model life cycle, which is something else, but it's also versioning. So this is how people deal with it. And then when you build, you build and you release this software in a different way nowadays, but still it is the software development life cycle. So the application build is just like DevOps concepts in software, and you have the code, and you write the code and you push the code in GitHub and so on, and you have this management of the code, and then you build the code and you test it and you put it in production, whatever this production is. But now it's also a big challenge that with all these tools, that's why people are going to the cloud, because the cloud gives you everything in one place. But now, for example, you are using GitHub, which is free. But OpenAI is money. OpenAI is somewhere. GitHub is here, and some part is on your computer. A lot of latency is going on here. And you have to manage all these things. For teaching students, it's also confusing, actually. So, for example, in our course, you have like a little bit GitHub here, and you have Jupyter Notebook on your computer. GitHub is there. Some people are using Google Colab, and then this is connected to somewhere else and management. So that's why people are going to the cloud, because it's easier. The GitHub and actually Amazon implemented everything in one place. So you go, there's something like Jupyter. It doesn't name Jupyter. It's named somewhere else, something else. It's Jupyter actually. And there is something like GitHub. It's not named GitHub, but it is GitHub, and so on. So they put everything in one place. So the build process, you have just like normal, but this is for a normal application. But when you have machine learning, you have like training, and when you have training, it's this is a kind of, we call it nowadays ML ops, or it's a DevOps basically. So you have the data, and you have the feature extraction, and you have model training. Still, you have the code here, like GitHub, GitLab, whatever, and then you have the code, but you don't have only the code, you have the data, and you have the features of the data, and you feed everything here, and you have the model training. And when you have the model training, you have the model, you have to evaluate the model and validate the model, and you put it in production basically. And inside the cloud, when you have a large system, you have even go deeper here. You have to record the metadata, which is like when you train the model, you have to keep the data of this training, how you train the model, because something might go wrong here. And then where do you record this? When you record this metadata, which is like, for example, you tune simple parameters, hyperparameters, anything you do, this is a metadata in the cloud, and you store it in this metadata store. And then this becomes very, very interesting area also. A lot of people publishing papers here actually. And you have the model registry. You have to register the model. What is the old model? What is the new model? And so on. So the versioning of the machine learning, just like the versioning of software. For example, the software, when you have version 1, you have version 1.1. When you have small change, you have version 2, and you have big change. So it's just like that in machine learning also. You have model version 1 this is our initial model, which is the random forest model, for example. But when you do something, you do some fine tuning of the random forest, you name it 1.1 actually, but it's random forest. But when you change it to XGBoost, you name it, for example, something else. And then with the fine tuning of XGBoost, you name it version 2, and so on. So you have this model versioning also. So when you have the model and everything is okay, then nowadays you have to deploy it. And actually deployment is the way you put the model into production. But we have another thing, we call it model inference, which is like, okay, you have a model, you trained, you tested, and everything is okay. You put the model, now you put the model for inference. It means that you test the model on a data that it didn't see before, and now you are inferring the model. Basically, you send an image and you get the result back. What is this image, and so on. And when you do this, the deployment is the process of making a trained machine learning available for use in production. And model inference function now is you can use it, for example, in sklearn. For example, train the model here, serialize it, for example, and then you infer the model. It means that you give you give, for example, 1 and 2 and to the model, and which feature you give. For example, you give 1 and 2, and the model will predict. If I give 1 and 2, for example, the model predict and say that the temperature will be 5, for example. Things like that. So this is how you infer. You input the data to the model and you get the result back. So nowadays we have also something in large system, which is the model as a service. So and this is something more available with the large language models nowadays also. So so when you put the model as a service, you have a model. This model is doing something for you, kind of prediction, whatever. Then you use this model as a service. Sometimes there is a model by for example by Google or Azure or whatever. You use this model as a service. But how you use it, for example, use this as a batch prediction. Sometimes we say batch prediction, and sometimes we use it as an on-demand prediction. So the batch prediction means that it's kind of when you have a large collection of data and you collect this data and you give this bunch of data to the model and say what is the prediction. But sometimes the data is streaming continuously. So this is on demand. The data is streaming, and when the data stopped, the model is serving nothing. When the data is streaming, the model gives you prediction. So if there's a machine in the factory and this machine is sending data, it means that the machine is working. This machine is sending data. The machine learning model do some predictions, say that the arm should go right based on the data, the arm should go left based on this data. But when the machine stops, the data is not streaming, the model is not giving prediction. So what is the life cycle, the machine learning application life cycle? Of course, we do a lot of design, and that is, if you remember, this is the requirement of the software. And we have the development, actually the code. We are writing the code, and a lot of deployment, which is the serving of the model. So this is just like a software. You do requirement, you go to the user, you ask the user how you want to the customer, how you want the software, what you want the software to do, and so on. You collect these things formally on a paper or a document, and then you come back, you do the machine learning, you have the data collected, for example, and then you do the development, you write the Jupyter notebook code and so on, you do the training, and then when you have a model ready, then you feed it to the deployment. So that's what we call it, development to deployment. So you develop the code until you put it in production, into deployment, not just keep it on your computer for fun. So this is the what we call it, development to deployment. And when you have this, I will come back to this, but when you have this, then the deployment strategy comes on also. Okay, now you have an application, and this application is using a model in the cloud, and this application is using version 1. And now I have version 2 of the model because there was some improvement. Now what should I do? One strategy is that the basic deployment, just discard the version 1, put the version 2. But actually, when you have production and you don't want to anything to stop, you have to do something. And one thing to do, for example, one strategy is this shadow deployment, in which you have the version 1 is working, everything is fine, not shut down. I put version 2 also, but I'm watching it as a human. And I get the parallel prediction. This is giving to the production, to the user, everything is okay, production is not stopped, but I get also this for me. And some people write code here for the output to verify that both outputs are okay or even better. And everything is okay, slowly change. This is the shadow mode. Another thing is that this canary mode, canary deployment, which is like you put the production like, like on and off. You put it there, you see how it works. If it works fine, then okay, collect the data, everything is okay. If not, come back. So you put a small part of the production on it, like 10%, 20%, and so on, until you go to the version 2 and you put version 1 in archive. But the problem with the deployment also with large language, with large model, is that, for example, you are using Python version 3.6, but when you go to Amazon to deploy, their Python is 3.9. And then the classic problem. That's why people are containerizing, putting it in production, and so on. So this is also a classic problem. Also, you are using some tools on something on your local computer or on your server. When you put it in production, there are other tools. So this is a classical runtime problems. Monitoring, also for large system, monitoring is very important. Monitoring basically means that you have the API and you have the machine learning model and you have the data pipeline, you have many other things, and you collect all these logs in the metadata. If you are in the cloud, in the standard cloud, you collect all these things in the metadata. And some people are using machine learning to look at this metadata automatically to discover something. So this is also, you do automation in the system, but everything is automated, but you are watching the automation by automation. So it's a kind of, this is the reality actually. So you created a machine learning model to watch the store of the data and the automation system. If some anomaly happened in the metadata of the automation, then it gives an alarm that your automation system has a problem. Drifting of data, the last few slides I want to mention here is the drift. Is that you have actually the input data and the output of the model. And we have two different things actually. We have data drift and we have concept drift. When
you have the input of the model, and the model gives you some prediction, or you have this file, and when you have this record, this is the output. This is the Excel sheet, let's say. This is the input and output relationship of your data. Sometimes this data is changing over time, and this is natural. So for example, climate change. The temperature of 10 years before was, so you cannot use the data of 10 years to predict the temperature now. The last, I mean, before 10 years to predict now, because the data shifted actually because of the climate change, and that is the data drift. But we have this concept drift, which means that before I mean, this relationship, this input and output changed actually. So this is the by time, not now, but by time, this is changed. So before, let's say that before 40 was considered the maximum temperature, but now 50 considered maximum temperature. So before 40 was the input and output, but now this relationship of data changed. So this is the concept drift and data drift actually. So if the data is drifting, if the model is robust, it doesn't make sense that much. But it's also a question, if the data is drifting slowly, little bit, the model should handle this. But if the data is drifting largely, then the model should be retrained. So for example, the data of 10 years before, maybe, for example, if you look at the data of 2000 and 2001, there is change, but the change is not that much, and the model can handle it. But if you look at the data of 2000 and 2024, there's a huge change, there's a huge drift, and you have to retrain the model because you cannot use the same model there. And that will take us to the retraining. And there's a big question in industry, how often I should retrain, because the retraining means money actually. If you are using Amazon or other services, when you retrain your model, it means you have to pay computation. So the retraining time actually is very important, because it means you are saving a lot of money. If you don't need retraining and you retrain, then it means you are losing money. It's just like power saving actually. It's just like electricity saving. So for the companies, this is a big question. So for big companies, for example, in Netflix, they don't care. They have a lot of money, so every week they just retrain. End of the week, retrain based on the data of last week, and then you have another model for this customer, and that's it. Because they are using Amazon Web Service, so they don't care. They have a lot of money. But if you are a medium-sized company and you want to save money, so it's a question, when should I retrain my model? And that's it. Retraining methods. You can do a lot of things for retraining. As I said, for example, two main approach. You just retrain the model on a new model, or combine the data and partially retrain. Sometimes you partially retrain, not the fully retrain, or this approach of Netflix, you just automatic retrain every time. Another thing is that you have this drift detection that one of our PhDs doing. For example, you monitor
the data is coming. You have this drift detection when you identify that if I have this much change, it is time to retrain. Otherwise, just keep an eye on it. I know there is some change, but it's not that important. The model is robust enough to handle it. But when it comes to some point that it's not, the model cannot handle it, then it's time to retrain. Yeah, I think I will keep 10 minutes for questions. I have 3 more slides. I'll put the slides, all the slides on the, actually I have 20 more slides, but that's enough, I think. Yeah. Any question?
So how do you differentiate between data and concept drift? Is it
As I said here,
is it straightforward to do so all the time?
there's one slide how to detect these things also. I mean, how to detect. For example, some methods are quite sophisticated, let's say. For example, like some statistics methods, you create statistics testing and continuously test the data. Sometimes you hold a window of data, like for example, 20, 200, 2000 points, and then you check these 2000 points based on some ground truth. And you say that, okay, these 2000 points are okay, means, so there are many algorithms actually to check. It is getting complicated with some kind of data also. So, yeah.
In an industrial setting, is it often, do they continually check up on these things? They are monitoring these things, or is it just sort of in the ideal case where you see these things?
No. So the drift can be used for example, anomaly detection also. It's not like only for retraining. So if the data is streaming and you identify, for example, is not only for retraining or something, but you identify the data is changing, then you can just give an alarm, for example. And there are many use cases for drift. It's not something ideal. It's something very useful, and can be used for monitoring actually.
You were saying it is integrated in the system and the system development, and it has many things in common with the software development.
Mm.
So does it affect all parts, or can you do some parts, in the same, use the same methods that you have in the past to do the define requirements and so on? Or that all the parts of the process
Yeah,
affected by
that's
this, or is it, you know what I'm asking?
yeah, that's a good question. So the thing is, there are 2 different things. One thing is that the requirement of software requirement in general, there is a very huge community of software requirement in which they do this formal requirement and they record the requirement. Some people write it in in natural language. There was another community using natural language processing for requirement elicitation, in which you have a huge document, you want to just simply get this. But now with this this AI, the problem is that there is, you cannot apply exactly the formal requirement, for example, for AI. So you have a requirement specifically for AI, which is like not exactly the requirement of software, normal software. So you have the software, the software should give something, but it's the AI is not like functional requirement. You cannot say that, okay, I have this data, I need this output, because you don't know actually. It's like the data is coming, I can identify what I need from the software, but which kind of functionality, it depends of the data and processing. So it's a kind of 50% is just like before, but 50 other percent you have to redefine requirement. And that's the case for testing, for example. There's software testing for AI now. A lot of methods are applied, but you have to adapt also with a lot of new things. So it's the case of security. For example, there is security, classical security. A lot of concepts of security is applied still, but there's security for AI, which is like there are a lot of new things to adapt. So that's the thing. Did I? And also software architecture, for example, the whole software architecture now is reshaping, you know, this requirement with there was this natural language processing for requirement engineering. This large language model and this generative AI destroyed that the whole area, you know, like now you give the requirement document to ChatGPT and gives you that's it.
Software testing to some extent. Your code to the.
Classical software testing, yes. Unit testing, for example. Yeah, exactly. That's the classical one. But now, okay, how you test the large language model itself? That's a big question. How they test it, actually. I was reading a lot of things about this large language model, how they test it.
Feedback system of some sort of.
They depend mainly on the feedback system, actually. They have this a lot of technique of responsible AI, for example, but it's quite is not mature yet. And so for example, in industry, when they develop, I was mentioning this in another venue, when they develop an application, they take like 6 months or 3 months to test this application formally. But for OpenAI, every 15 days, they update the model and they put another model. I don't believe that they test in 15 days. So with all this data, I think 15 days is just enough for retraining the you know the ChatGPT, and how much time they take for testing. It's just
But this time depends on what the time you're saying.
time of testing or the retraining.
Say you're saying 15 days, but it depends on what number of GPUs or.
Yeah, it depends on the data centers and GPUs and so that's the thing. Yes. Come on. Yeah. Yeah, exactly. Yeah. So what I saw for this tiny ML, I'm not expert actually in this, but what I saw from this tiny ML is used with this federated learning a lot. So there is a standard machine learning model and there is this tiny ML. Another thing is that these are used a lot for IoT actually. When you have a device, a refrigerator, and this refrigerator has like limited functionalities, limited sensors. These sensors are sending limited data, and there's, like limited cases. And they just train this on limited cases. If this happened, that is the case, and so on. And they put it in that device in production. Some I know that some devices they put it in production, and that's it. It will be there, and if something happened, they send some technician with some flash memory or whatever, and they update it. Some others they are connected to internet, and they manage it this over the air, and they update the models. Another use case of the tiny ML is like these small wearable devices they use in wearable devices to detect something for elderly people, for example. So that's also some use cases of tiny ML, yeah. Okay. So do we have record of this, is it?
Yes.
Oh, okay.
Okay, so.
I'll put the slides, and we will
Yeah,
put the
we
records
will-
there.
yeah. Okay.
Thank you very much.
Thank you.
Thank you very much.